Hey guys, as I had said earlier this morning, I'm going to show you a presentation of the generation to meter project that I had for you as an example. So let me bring it up here. All right, there you go. Michael Woolison here, he created a cover screen in the beginning which has it titled and his name, and he's got a nice little beginning schematic here or drawing graphic of generation to the meter to the house. Okay, the first component is going to be the generating station. And a generating station works by converting a different power source into a mechanical energy, causing a turbine to spin in a magnetic field with conductors creating alternating current electricity. So you need movement, current, and voltage. Movement and current, of course, are going to make your voltage. We've learned that already. Different power sources are nuclear, wind, solar, coal, hydroelectric, and gas. Right after it comes out of the generating station, you see this red arrow here, it's going to go into what they call a step-up transformer. We're generating at a lower voltage, not a transmission voltage, to be able to insulate a lot easier, and it's just easier to get out of the generating station, off the generator, to this transformer at those lower voltages. The step-up transformer then is used to increase the voltage from the generating station so the voltage can be transmitted more efficiently across a long distance to the next destination. Our next piece right here is what they call a switch yard, used to redirect and add more transmission lines depending on the direction of travel and how many transmission lines are needed. Can be used to turn a circuit on and off, so we can, it's like a train station. We can divert and send power in multiple different directions. Here in the switch yard, transmission line just doesn't go to one location. And you can actually see, here's a switch yard over here, and there's transmission lines over here. So you know it's going multiple directions. That's what a switch yard does. Our transmission lines, they are used to transfer the extremely high voltage to transmission or distribution substations. Use a smaller gauge wire due to the low amps, making it cost effective. Well, we're transmitting at such a high voltage that our amperes are lower, and they're able to use a smaller conductor. A distribution substation, so we're coming off the transmission into the substation. It's used to convert and redirect the transmission voltage into distribution voltage for residential area use. So we've transmitted from a long way away here on the left-hand side in transmission. We come into the substation, we have a substation transformer, and we're going to step down the voltage, and we're going to go out to these distribution voltages right here. You see 7.2 kV, 7,200 volts. Because they have to go shorter distances, for one, and two, they're easier to convert for the voltage that's going to be going into your house. As we spoke of before, in the substation, there's a step-down transformer. So we've got transmission voltage on this side, distribution voltage on this side. Right in the middle here is a step-down transformer. That step-down transformer converts the high transmission voltage into the distribution voltage by converting the electricity into a lower voltage. So we're doing on a real large scale here. You've seen transformers that we've had in class. Those are typically like a 25 kVA or a 10 kVA or 15 kVA. These transformers will go up to 22 MVA, so megavolt amperes. A bus bar. Well, once we leave the transformer, we're going to come off the transformer with conductor or bus, and this one's using bus bar, as you can see right in here. A bus bar distributes and redirects electricity inside the substation with great ease and efficiency. Bus bars, because they're solid pieces of metal and they're tubular, they're able to carry a high amount of amps. So that's why we use them inside of substations. A distribution breaker. Now we're getting ready to leave our substation and go out on our distribution lines, so we need some type of protection. A distribution breaker can be used to de-energize a circuit if maintenance needs to be performed, and it also protects the circuit by opening the circuit through a switch if a fault occurs. So if a power line falls to the ground or the tree falls on it or something like that, we don't want it to burn. We want it to trip out just like a breaker would in your home. So it protects against overloads, faults to ground, and transformer faults. After we leave the breaker, we need to regulate the voltage so it stays within the plus or minus % that we need to have in our system. So it maintains the distribution voltage at the acceptable range of operation, provides consistent voltage value on the output side, and as I said before, plus or minus 5%. So if we're coming off the breaker at 7,200 volts, this is regulating the voltage to be plus or minus 7,200 volts, voltage regulator. Feeder line, main line. These are the lines that come directly out of the substation. The main lines are the power lines that come out of the distribution substation that are at the appropriate voltage for residential and commercial use. So these come out of a substation and they're going to go along the highway and by businesses and into subdivisions. This is one more step beyond this, and then we'll have voltage at our homes. All right, off our feeder line, we can have tap lines. So we can tap off the feeder if we need just to go a short distance and feed a small load off to the side here. So a fuse tap is a power line coming off the main line to direct some electricity in a different direction than the main lines. A fuse tap has a switch with a fuse to provide circuit protection to the main line if a fault occurred downstream of the tap. So what we hear is we have line protection here. If a tree fell on this, or if this fell to the ground for some reason, or a storm happened, it would blow the fuse. And our main line, feeder line, would stay intact. It would stay on. And that's why you're going to have a fuse tap. They also have what they call a solid tap. Now I'm going to use the previous picture here. If the fuse was not present, and you will find this on some systems, if I took a piece of wire and just connected it from the tap line directly to the primary and didn't include this switch and fuse, that would be a non-fused or a solid tap. Now the problem with that is if I have any kind of problem here on my tap line, tree falls on it, it falls to the ground, not only is it going to be a problem with the tap line, but it's also going to take out the entire feeder because the breaker will open the substation. I don't have any fuse protection on a solid tap line. Step-down transformer. Well, above here, we're at our distribution voltages, and we used 7,200 a lot before. But now I need to get it to a voltage where I'm able to bring it into my home. So I've got to have one more transformation process. This transformer is used to convert the main line voltage or distribution voltage into a lower voltage, 240 and 120, for residential and commercial use. If I'm coming off the transformer, or I'm feeding from the transformer down to homes or down the street, I need, from structure to structure, I'm going to need to have secondary lines, and these are those lines that you see in this picture right here. Now the secondary lines, as I said, go from structure to structure, and they're at secondary voltages. The line that comes off the structure anywhere and comes to your home, to the meter itself, is the service line. And the service lines span from the transformer or the secondary lines to the meter. And last but not least, we come to the meter base, and the meter measures the amount of electricity that's being delivered and used in your home. So that pretty much wraps it up. If you have any questions, we have the full week to complete this. These are due next Monday, and I hope you guys do well on your PowerPoint or whatever type of presentation you would care to make. Thank you very much. Have a nice day.